So today's lecture is about three-phase induction motors. To start with, we'll do an introduction about the use of motors and the classification of motors. Then we'll discuss about the operation of three-phase induction motors, the principle behind them, the physics behind them, how they are designed, and the various applications that they have. So let's get started with an introduction to the types of motors. So now, motors are some of the most useful applications of electrification in the world. So the whole unit we've been discussing the whole process of electrification. So from generation to transmission and distribution. Now we are looking at the various applications of electricity as a source of energy. And within these applications, one of the key applications is motors. Electrical motors convert electricity into kinetic energy or mechanical energy. It is a way of transmitting power from one place to another and having electrical, or rather mechanical or rotational energy available at the exact position where it is required. It's a very clean way of rotating machines, and they are there's a very large array of the types of motors, from huge megawatt motors to tiny micro motors. So the types of motors are what I'm showing on the screen. So you have electrical motors are basically divided into two. You have AC or DC motors. DC motors, I believe you already covered in a previous unit. That was the introduction to electrical motors and electromagnetic principles of motors. In this unit, we will mainly be covering AC motors. So AC motors are divided into two. We've been talking about three-phase or single-phase power. So we'll talk about both types of motors. Both types of motors exist. You can have motors that make use of three-phase power, and you can have motors that make use of single-phase power. Three-phase power is used in industrial applications and heavier applications, while single-phase motors have usually lighter duty, and there's a vast array of those. So as you can see, single-phase motors have very many different types or designs or criteria. This classification is based on the principle of operation of these types of motors. And in this case, we will be looking at three-phase and single-phase motors. And the three-phase motors we'll be looking at are what we call squirrel cage general purpose. These are also known as induction motors. Induction. The reason for that is, as we shall see in the rest of this lecture, is that we make use of the principle of electromagnetic induction to create the mechanical power that we are talking about, or the torque that we are talking about. This principle of induction is also used in some single-phase motors. It is used in shaded pole motors. It is used in split-phase, capacitor, and repulsion start induction run motors. So all these types of motors, shaded pole is slightly different, but these three types of motors are induction motors as well. So you have the most common, which is three-phase induction motors, and you have some single-phase induction motors. So under those, we have split-phase or capacitor. We shall look at those in the next lecture. And we shall also look at shaded pole and universal. We won't go into synchronous motors in this unit. Likewise, we will go into soft start. And another type of motor that we will also not look at is reluctance motors. These use the principle of attraction of magnets, which will not go too much into because they are not very widespread, right? Before we go into this, because as you can see, induction motors are the primary type of motor that we are talking about. We can talk a bit about synchronous motors. Synchronous motors are related to the alternators that we looked at the beginning of the unit. So they rely on the same principle as the alternator. The only difference is that whereas the alternator had a field and was fed with mechanical energy or rotational energy, and the field was rotated within some windings, for a synchronous motor, you have the field applied to windings in the stator which are already electrified. So it works in the reverse of alternators. In many cases, actually, synchronous motors and synchronous generators are the same machine. That is, the operation of the machine depends on whether you are inputting mechanical energy or outputting mechanical energy. That's the only difference in the machines, because they have a field winding being rotated inside an armature, right? So at that point, that's the brief introduction of motors. So usually what happens is, the reason why we are starting with three-phase induction motors is that there is a principle. So we will start with three-phase induction motors. They're called squirrel cage. I'll explain why shortly. But the reason why we start with those is, first of all, they are induction motors, and secondly, they are what we call self-starting. Three-phase induction motors intrinsically in themselves are self-starting. I'll explain that a bit later on within this lecture. But because of that principle, it is more logical or more convenient to start with the three-phase motors, as their principle, I would even say, is simpler to understand. Their principle of operation is simpler to understand than the single-phase motors, which we will cover in the next lecture. Okay. So before we dive into three-phase motors, let me just let in some more students. Okay. Is anyone else waiting? I see we are up to 16 people. Okay. So let's continue. Okay, so three-phase induction motors. So what you're seeing on screen is a typical three-phase induction motor, what we are calling a squirrel cage induction motor, right? Three-phase. This type of motor is what I would call the workhorse of industry. Everywhere you go, any kind of application that requires any kind of larger scale work, and in some cases even low scale, small scale work, will use this kind of motor. These are three-phase induction motors. And the reason why they are so widespread is that they are very simple in construction. What you can see here, there are two parts. Here we have the stator, and here we have the rotor. So there's a rotor there and a stator there. So far, very similar to all the electrical machines that we've seen before. But the main advantage comes here. If you look at this and inside there, let me draw it here. Inside there, you will notice that there are two bearings. Yeah, usually ball bearings or thrust bearings. Standard industrial bearings, very durable, usually greased for life. They don't need any maintenance. They don't need any lubrication. The reason why three-phase induction motors are the most commonly used and most widespread motors in the world is because of this construction. The only moving parts, the only things that experience friction within the motor are these two bearings. Now, anybody who is designing any kind of engineering application knows that the biggest source of wear and tear and maintenance is friction between moving parts. So if you have a machine which only has two moving parts, the two bearings, you will have very little maintenance required for that machine. That means your machine, first of all, has little maintenance, and it will be robust. Okay, little maintenance in that the only thing that can fail generally mechanically is the bearings, and that's the only thing that you need to look at. And it is robust in that because this is a fairly simple design, it will be rugged and there'll be very little wear and tear, so you'll have a long lifespan. So that explains the widespread use of these motors. So let's go into it a bit deeper. In the stator side, you can see these copper windings. We'll zoom in a bit. These copper windings, as you can see them, form the windings of the stator. And if you notice, you can see here, they are kind of moving in that direction and moving in that direction. So these windings form loops around here. They should be roughly around there. So they will form loops of windings around the surface of your stator, and likewise over here. So they move all along from the front to the back. So you can see each set of windings is a coil with many strands within it. If I zoom in a bit more, many strands within it that go through to the back of the stator itself. So if you look at it, the stator is essentially a tube or a core on which these windings are mounted. And if you look at it, there are various, I can call them teeth, but they are usually called the yoke of the winding. So the cross section of that would look something like this. So you have that, then you have little, drawing is not very good, but you get the picture. Something like that. Okay, so you have little teeth along which the windings are placed. So you'll have your windings within the core going through from front to back, looking like that, right? Which is what we are seeing over here, going from front to back. So at the back, you have similar ends that look like this. So there will be three sets of windings which will be mounted onto the stator. And these three sets of windings are connected up here at the top on what we call the terminal. Let me change the color. Terminal box. So terminal box. Right? You can see there are three connection points at this terminal box. So here and here, here and here, here and here, right? Usually we call this U1, V1, W1, and W2, V2, and U2. Reason for that is each set of windings. So like, for example, this winding that we have here, these ones that are grouped together, that seem to be following the same kind of path, would all be connected together at each, along the terminal box at the two ends. They'll be connected together at these points, right? So that the coil has two windings. So every set of windings has two ends. And then there are three sets of these windings that are put together. And each of these three is connected to a phase of the power supply, right? So you have three-phase power supply being supplied to your windings, and the windings will become energized inside the stator. That's key number one. Key number two. Remember, this motor is called an induction motor. The reason why it's called an induction motor is that the interaction between the windings in the stator and the windings in the rotor, the stator and the windings in the rotor is through electromagnetic induction. So electromagnetic induction. This is the principle of operation that is used in the three-phase induction motor and indeed in the single-phase induction motors as well. We said that there are no moving parts within this kind of machine. In the alternator, we had slip rings that were used to connect the field to a power supply. Here you have noticed that I said the only moving part is the bearings. There are no slip rings. That means there is no electrical connection between rotor and stator, right? There is no electrical connection between the two. So the rotor will rotate. It is free to rotate inside this space within the stator, but it will never come into physical contact or even electrical contact with these windings. The way in which these two interact is through electromagnetic induction. So what will happen is in your rotor, you will have things that look like bars. Here they are not very well defined, but essentially, as you can see here, there seem to be some lines that are moving across the rotor, skewed, along the rotor that are skewed. What these are actually copper bars that are inside the rotor, and they are short-circuited at the two ends of the rotor. This is actually a winding. Even though there are no wires, instead of wires, it makes use of copper bars, thick copper bars that have current flowing through them, that allow current to flow through them, right? The only time when you can have electromagnetic energy transfer is if you have an electric field interacting with current carrying conductors, and therefore you need current carrying conductors within the rotor. Okay. Actually, you can think of the electromagnetic or rather the induction motor as a transformer which is free to rotate. You can think of it as the stator being the primary, which is supplied with power, and the rotor being the secondary winding, but with the only difference that it is free to rotate, while on the other hand, there is no output in terms of electricity. There is no, the windings are shorted within themselves. They just carry the current within themselves without supplying any external load, right? So I think that is mostly what all we have to do with the construction of the three-phase induction motor. Let me see if there's anyone else who is joining. Okay. Right, so we've looked at the types of motors. We've looked at the three-phase induction motor. Let's look a bit more into the construction of the three-phase induction motor. So this is an exploded view of the motor, which shows some of the parts that we've been talking about already, that we have already mentioned. So you have number 9, which is the stator assembly, which is over here. You have your stator assembly, right? We've already talked about that. In the stator assembly, you have the windings which are mounted within, running from front to back. Admit somebody else. Okay, running from front to back. Number 4 here is the rotor, which we've talked about. Excuse me. Here, number 3, and at the other side, there's a corresponding similar component, is what we call the end shield. This is what holds the motor together. In our photograph here, that would be this component there, right? Of course, your rotor has a shaft which allows it to be connected to a mechanical load outside the device. And that electrical or rather mechanical load can be connected or mounted onto the motor through a flange or a flange, whatever the pronunciation. Here we have some more components. This is the terminal box, which we talked about. And we said it will have 6 terminal connections, 2 for each set of windings. So 2 connections, very thick, for each phase. Okay, each set of windings is connected to a phase of the machine or a phase of the power supply. At the far end here, you have a fan. The fan provides cooling to the machine as it is operating. And then you have various other components. So this is a bearing. There are 2 of them. There's a bearing on this side as well. This is a bush, a spring bush. Then you have number 11 is a retaining ring, and so on and so forth. There are various other components that you can look at. I will share this diagram and you'll be able to see what the components of the 3-phase induction machine are. So now let's move on to the principle of operation. We've already mentioned that it uses the principle of induction. So it uses induction. And there are 3 or rather 2 main principles that we will really need to understand in order to understand induction motors in general. So both 3-phase induction motors and single-phase induction motors, this is a key principle. And if there's nothing else you get from this unit after the exam, nothing else remains with you, I'd really like you to at least be able to understand this principle of 3-phase induction motors. Like I said, 3-phase induction motors are the most widespread electrical machine you will find out there in industry. Those of you who will go to industry, those of you who will become engineers, eventually you'll become senior people in your organizations. This is one of the key things that you need to understand about the machines that you'll be working with. Whatever the application, whatever it is being used for, the underlying principles of motors within industrial applications are what we are talking about right here, right? The windings, what we're going to talk about, rotating magnetic field, how that rotating magnetic field generates torque. Those are the key principles that I'd really like you to take home. So the principles of induction are 2. Number 1 is rotating magnetic field, and number 2, torque creation. Okay, so let's start with rotating magnetic field. Right. So rotating magnetic field, anytime you have a current carrying conductor. So let's just start with that. Anytime you have a current carrying conductor, a wire that is carrying current, right? Say the current is going in that direction. What will happen to this wire, as long as it is carrying current, you will have an electromagnetic field, or rather a magnetic field being induced around it. And the direction of that magnetic field is determined by the rule that you're seeing there. This is called the right hand grip rule, or Ampere's law. It is determined by Ampere's law. So this is your right hand. So what happens is the thumb points in the direction of the current, and your fingers going around that current carrying conductor, wrapped around that current carrying conductor, determine the direction of the field. So in this case, if you place your thumb pointing upwards, your fingers in your right hand will point in the direction that is shown. So it is a counterclockwise direction. Counterclockwise. Okay. This is the first principle of the operation of the three-phase induction motor. The fact that a conductor that carries current, that is carrying current, creates around itself a magnetic field that is determined, whose direction is determined by the direction of the current. So if your current was flowing downwards, you would have an electromagnetic field that would be going in a clockwise direction. Like that. Okay. And this is the first principle of these things. Now, in order for us to explain further, there's just a bit of notation that I'd like us to understand. In terms of going upwards or downwards, that is clear. But in case we would like to illustrate conductors with their cross sections, it is useful to note the kind of notation that we have with regards to cross sections of conductors. So in the case of the cross section of a conductor, you can either have current flowing into the conductor, or you can have it flowing out of the conductor. Think of it as an arrow with the X showing the arrow moving away from you and the dot showing the point of the arrow moving towards you. So this is cross section of conductors. Yeah, they look like that. And of course, by our principle, if you have your thumb in the right hand, you will then be able to see the fields that are created around the windings will be such that in this case they are clockwise, and in this other case they are anti-clockwise. Right. Clockwise, anti-clockwise. Okay. So that's the principle of Ampere's law, whereby a magnetic field is created around a conductor simply because it is carrying current. So that's principle number one. So now let's look at how that is applied to your motor. Remember, your motor consists of very many windings. So each of these little lines here represents one wire that is carrying a current. All right. So each of those is an individual current carrying conductor, and the cumulative effect of all those conductors is what leads the induction motor to perform its operation. So let's look a bit further at how these ones will look. Now, let's say you have a three-phase electrical voltage or electrical current that is applied as we have seen here, right? Remember last time we talked of three-phase voltage is in consists of three phases that are 120 degrees out of phase with each other. So if this represents a graph and this represents time, and this axis represents we can call it the magnitude of the current, right? So what you will see is you have three phases, call that red, blue, and this is yellow, but we've indicated it in green. Generally, that would be the third phase, but green shows up better on the screen. So assume those are our three phases. So you will see that blue reaches its peak at a time before the green or yellow and before the red. And the gap between these two is 120 degrees of the cycle. Okay, let's remove that for now. Right, So that's principle number one. Then number two, let us assume the red phase is connected to a certain winding of the motor. So like if it was here, we would assume that you're connecting your red phase, let's call it U1, U2. So the red will be here and its output will be there. So this is red 1 and red 2. Likewise, say blue would be connected here. That's blue 1 and then blue 2. And finally yellow, call that yellow 2, and that would be yellow 1. So what happens is you connect each of the three phases to a certain end of the windings. So the red would enter the winding through here. It goes, circulates inside the motor, and it will come out at this end as red 2. Okay, which is what we are talking about over here. Right? So here we are talking about red, blue, and yellow being applied to the induction motor. So now these circles that we are seeing here, let these represent cross sections of the motor. So cross section of the motor at different points in time. So at instant number 1, we have your motor being represented here, right? So let's look at how the currents would be indicated, or how the currents would be flowing at instant number 1 within the motor. So at instant number 1, how would the motor windings look like, right? Now, for purposes of this illustration, let's assume in the upper side of the windings, let's do it over here, not the windings, the upper dimension of the voltage or the current here. If you have a current flowing with this magnitude, right, this positive magnitude, let's assume in terms of our cross section here, that current is flowing into the surface. So we'll give it an X like that. And in terms of the negative on this side, let's assume it is flowing out of the circuit. So negative equals out, positive equals in. Okay. So that's what we are looking at. I hope we can all see that. So in the case of instant number 1, so let's zoom in a bit on instant number 1. So instant number 1 is here. Try and make it centralized. Okay. Instant number 1 is there. So now let's look at the currents that would be flowing in this particular instant, right? This is one cross section at time t equals 1. Okay. Now at time t equals 1, the red phase on the positive winding, let's call this the R1, B1, and Y1. The red phase on your positive terminal, let's say it is here, let's call that R1, would be into, because it is here, it is positive. Yeah, let's draw it on this side as well. It would be into this winding. So it is an X over there. Okay. Blue is at 0 at this time. So there's no current flowing through at this particular instant. And yellow, because it is in an opposite polarity, would be flowing out of the winding. So red is here, blue is 120 degrees away. Sorry, let me mark them the same. Blue end number 1 is there, and yellow end number 1 is there. So yellow, we have said, is flowing out of the windings, right? So it is there. There. Okay. Right. Now, remember, these windings are all connected to each other. So the inward or supply point of red will come out at the opposite end as R2. The first end of B, the opposite end is B2, and the first point of Y, the opposite end is Y2. Remember, we are talking about the terminals that are here. So we have R1, B1, and Y1 here. Then we had R2, B2, and Y2, B2, R2, right? So there's an R1 on one side and an R2 on the other side. That's what we're talking about over here. Right. So if you have a current, that one has slightly shifted. I don't know. Sorry. I don't know what has happened here. Okay, so it's back there. Okay. So if you have your current in R1 on this side being into the winding, on the opposite end, it will come out of the winding, right? Likewise for Y1, if you have the current on Y1 going out, on the opposite end, it will go in, okay? Now, this is the state of the currents that are flowing within the windings at this particular instant in time, okay? So now during this time, you have currents flowing as indicated. So now we go back to our Ampere's law and we say that in the case of a current that is flowing inward, you get a clockwise magnetic field, and a current that's flowing outward, you get anti-clockwise magnetic field. So the outward ones have anti-clockwise magnetic fields. So they move that way. Right? Remember, this represents the cross sections of the windings within the induction motor. Okay, so they are moving that way. These other ones are in clockwise directions, so they would move that way. Clockwise, moving that way, right? So if we zoom in a bit more on this, you'll notice that on the left-hand side, R2 and Y1 have currents which create magnetic fields that are moving in this general direction. And on the right-hand side, inside the space of the stator, you have a magnetic field that is moving in that direction. This means that the resultant magnetic field at time t equals 1, simply because of applying a current or a voltage, will move in the direction indicated there. Okay, so let's show it moving clearly like that, right? At time t equals 1, by applying a current, the resultant magnetic field will be in the direction shown. Now let's look at time 2, right? Time t equals 2. At time t equals 2, you have your currents looking like that, okay? So your red, blue, and yellow at that particular instant look like that. What does your red look like? Previously, R1, let's indicate them here. So they are the same cross sections, R1, B1, Y1, and R2, B2, and Y2. Same cross section, just a different instant in time. So this is time t equals 2, right? A few milliseconds later, you have the voltages or the currents have changed, because the red at time t1 was positive, but it is now at time t2 0. So there's no current flowing in the red. Blue at time t1 was 0, but now it is positive, which means that B1 will have a positive current. So it is an X there, right? Red, there's no current flowing through, so we indicate nothing there. Blue, there's a current flowing through. It is positive, so in our diagram, we indicate it as going in. And yellow, in time t1, it was positive, rather negative. Time t2, it is still negative. So it is a negative current there. Same principle as before. When they go in one winding, one end of the winding, the other end, they go out. If it is going in on the other end, the other side, it is going in that direction. So that means that your magnetic fields that are formed by these currents will look like this. So your positive ones are anti-clockwise, so they look like that. And these other ones are going in a clockwise direction, so they go like that. Okay, so that means that if we zoom in here again, you can see that inside the stator, remember this is the cross section of the stator, inside you seem to have the magnetic field moving in that direction. So what you find is your resultant magnetic field is now in the direction that way, right? Red had no current, yellow and blue had currents that are positioned in that way, and then you will find that you have a resultant magnetic field inside the stator at a direction that looks like that. And you can proceed on to do the same sort of thing at every particular instant that you would like. At any given instant, you would then find your windings would have different directions. So in point number 1, your direction is upward. Point number 2, it is going to the left. Point number 3, it is that way. Point number 4, it is down like that. Point number 5, it is like that. And by the time you're getting back to number 1, it is up again. Okay, so sorry, point 4 would be slightly down. Point 5 would be in that direction. Point 4 is there. Point 5 is there, right? So what this means is, as you move from one point to another, the resulting magnetic field inside the stator changes direction around the stator itself, right? So it's like you have a magnetic or a magnet that is mounted inside the rotor or inside the stator, inside the space of the stator, that rotates around the space of the stator. So if this is your stator, and when you apply your rotating or you apply your voltage, red, yellow, and blue, it will create a magnetic field that will move. It is in this direction, but it will rotate around the stator. So this in turn creates your rotating magnetic field, right? This principle, what I have just explained, that you have simply applied an electrical current to the stator of the machine, and by simply applying that current, because of the way the windings are mounted along the stator or along the core of the machine, you will then have a rotating magnetic field. Without physically moving anything, without applying any mechanical energy, you have a magnetic field that, in the eyes or from the perspective of the motor inside the machine, you have a magnetic field being rotated. It's almost like you have a magnet that you are rotating, similar to what we had with the alternator, a magnet that you are rotating inside the space of the stator. So that's principle number 1 of your induction motor operations. Okay, you have your rotating magnetic field. Okay, well and good. You have a rotating magnetic field. How does that translate into mechanical energy. Why is it so important, right? Remember that this rotating magnetic field is an intrinsic property of your three-phase current, right? It does not require anything except for the mounting positions of the windings and a three-phase voltage or current applied. Now, we go back to a bit of physics. Okay, how do you create force when you have a magnetic field, right? So we say that in the case of a rotating magnetic field, or in the case of any current carrying conductor that is found within a magnetic field, right, you will have a certain reaction governed by Lenz's law that will create a thrust of motion. So when you have a field and a current, here with your left hand, this is in turn left hand rule, there is an interaction between the field and the current that is flowing in the machine that will cause a torque of motion. So now let's look at in any particular place. So you have, let's say, you have your rotating magnetic field that is moving inside your machine, moving, say, in that direction. You have your windings that are here, and now we put into play the rotor, which goes in there, right? Now the rotor itself, if we were to draw a cross section of the rotor, let me start with the stator. Try and draw a better circle. If that is your stator with its inner core, so stator, and you have your rotor mounted on the inside of your stator. Okay, so your stator looks like that. Right, and your rotor consists of, we talked of, copper bars. So this is a cross section of what the rotor would look like. This is a cross section of the rotor mounted inside your stator. Okay, now remember we said we have a rotating magnetic field that at any given time is in a specific direction. So it looks like north to south. Say if this is north and that is south, it looks like your field, the magnetic field, is in that direction, but the magnetic field itself with time moves along the stator. So this north will tend to rotate around the stator from one point to another. Your rotor is mounted inside the stator, but it is free to move. Okay, so let's zoom into some of these copper windings. So you have, if you look at these, not copper windings, the copper bars. Okay, if you look at these copper bars from the perspective of the copper bars themselves, right? You have a copper bar which is mounted inside here, and it is experiencing, from the point of view of that copper bar, it is experiencing a magnetic field that is moving in a certain direction. Because this is a rotating magnetic field, it is moving in that direction. So it is like the field is cutting across the windings themselves, or the bars themselves. So the same principle applies of electromagnetic induction. What will happen is you will then now have within the copper bars, you start to see a current flowing inside the copper bars due to the magnetic field that is there. Okay. Now, in that particular case, yeah, you have magnetic field which was created from here, your rotating magnetic field, which was created from the action of the windings in the stator having power applied to them. That rotating magnetic field is moving through the rotor, and it has now induced a current within each of the rotor bars, right? These rotor bars are like wires. They are like any other conductor. They will conduct current, okay? So let's now look at what will happen when that particular instant occurs. So now you will have your left-hand rule coming into play, because what you have now is something that looks like this. You have your field, okay, in this case, it is in the opposite direction from what I drew. You have your field, say, going from up to top to bottom. Inside your rotor is here. And then your bars have currents that are flowing within them. So now if you look at, let's pull this down. Let's bring this a bit down. So if you look at it from that point of view, you have your left-hand rule. Sorry. You have your left-hand rule, which states that if you put your fingers at right angles to each other, so the index finger is pointing to the direction of the field. This is your index finger. Your current is at 90 degrees to it. It is the middle finger. And your thumb will point in the direction of the thrust or force that will result. So you point your index finger in terms of in the direction that the field is flowing. So the field itself is moving in a downward direction, okay? You don't look at the direction of the north to south. Okay, you look at the direction of north to south. So it's pointing downwards. The field is pointing downwards, right? So you orient your finger, your first finger downwards. The current that is flowing inside the rotor this time, remember the induced current that we had, is flowing into the surface of the screen in this case. So you point your middle finger towards the screen. That leaves your thumb moving in the direction that the force is moving. So the force is that way. What this means is that you have the rotation of the electromagnetic field, the rotating magnetic field moves in the same direction as the force that will be acting on the rotor conductors, okay? Because you have the field from the rotating magnetic field, you have a current that is induced, you then have a resulting force that is acting on the conductors in that direction. Let's put the force in red. So the force is acting on all of these in that direction. And because your rotor is free to rotate, if we go back here, because your rotor is free to rotate, that force will tend to take it that way, okay? And on this opposite end, you would have the windings, because generally the windings would be in the opposite direction. You'd have your force in the direction that is opposite. So the bottom side will see a force in that direction, and the top side will see a force in that direction. And remember, your rotor is mounted on bearings. So what happens? It then begins to rotate in the same direction as the direction of the rotating magnetic field. So what this means is that as long as you have a difference in the speed, how do you put it? A virtual difference in speed between the magnetic field and the mechanical motion of the rotor, there will always be a force between the two, or rather a force on the rotor. So the RMF would move in one direction, and the force or torque would move in the same direction. And the RMF would move at a speed which we call synchronous speed. The torque would cause the rotor to move at a speed n, which is the mechanical speed. Okay. At any given time for an induction motor, the synchronous speed will always be greater than the mechanical speed, always. Let's look at why that is. The reason for that is you must always have the field interacting with the current itself. Okay, you must have the field interacting with the current that is moving within it, right? There has to be a direction in which this is rotating. There must be a relative motion between the magnetic field and the current carrying conductor, right? The field must cut the conductors, right? It has to move across the conductor. And if the speed, synchronous speed was equal to mechanical speed, the field would be moving at the same speed as the conductor, and that would mean that it would be having no difference between the two. Therefore, we must have what is called slip. And slip is equal to S, which is the synchronous speed minus mechanical speed over synchronous speed times 100%. So this is the difference between the two over the synchronous speed. And for induction motors, this is between 5 to this depends, it will be 2 to 5 or 6%. Yeah, for induction motors, the difference between the speed of the synchronous the speed at which the magnetic field is moving, the rotating magnetic field, and the mechanical speed which the rotor moves at. And the synchronous speed is a factor of two things. It is a factor of the frequency of the voltage, that is from this point to this point. What is the time taken? Yeah, what is the frequency? In Kenya, that is 50 hertz. So the frequency of the voltage supplied over the number of poles. So the poles will be, in this particular case that we had here, so you can see there would be 3 sets of windings that are indicated here, right? Generally in this one. So this would mean that each of these would have a corresponding set within the two. If there were 6 sets here, you would have 6 times 2 number of poles, right? So the number of poles that are within the windings, right? So this is frequency and poles in machine. Okay. So those are the two determinants of the synchronous speed. Now, one key element that we talked about and we kind of glossed over, we mentioned that there is an induced current within the rotor. So the rotor has a current induced within it, rotor current. And this current has a frequency that can be shown to be the frequency of the rotor current is given by ns minus n. That is the speed of the rotating magnetic field minus the speed of the physical rotation of the rotor times the number of poles divided by 120, right? And if you remember that slip is ns minus n over ns, you can say that, bring this down here. Because slip is equal to ns minus n over ns, you can say that SNS equals to ns minus n, which we can bring there. So in other words, the rotor current frequency is equal to S times ns times P over 120. Ns is the synchronous speed. S is the difference between the ratio between the difference of mechanical to rotational, or mechanical to rotating magnetic field, the speed of the two, times P, the number of poles, right? This tells us that if, for example, the frequency of your, or rather, if, for example, the synchronous speed of your stator rotating magnetic field is, say, 1500 RPM, yeah, your frequency within this particular rotor will be equal to S times, remember that is the frequency here, okay? Because ns, this can be converted into you can rearrange that to be Fs is equal to ns times P over 120, which in turn is what you're seeing here. So the rotor frequency is S times the frequency of your supply, okay? So the speed or the frequency of the current that flows within the rotor bars is equal to the slip times the frequency of your supply. It means that your frequency is 2 to 5%, frequency in the rotor is equal to 2 to 5% of that in the stator or in the supply, right? So it rotates at, it fluctuates or pulsates at a much slower speed than what is there within the supply, okay? Let's look at a brief example of, what we've talked about, the principles we've talked about. So let me bring in that. So here we have a machine, a motor that has a slip of 5%. Calculate the following at rated load. So we start with synchronous speed. So now the synchronous speed we've already talked about. We've said synchronous speed is given by ns, which is 120 F over P. In this case, we've been told the frequency is 50 Hertz. Number of poles is 4. So it's 120 times 5 divided by 4. Sorry. 120 times 50 divided by 4. So it is 1500 RPM, right? That's your synchronous speed. Number 2, the rotor speed. So we know that rotor speed, or rather slip, is given by ns minus n over ns. If we convert this so that we make n the subject, we will get s ns. Actually, we forgot the percentage. So times 100. So SNS over 100 is equal to ns minus n which then becomes N equals NS into 1 minus S over 100, right? Therefore, N is equal to NS was 1500 into 1 minus slip was 5%, so that is 0.05. So it's 1500 times 1 minus 0.05. So this speed of the rotor is 1425 RPM. So this is what we are talking about. The synchronous speed, the speed of the rotating magnetic field is 1500 RPM. But the rotor speed, the mechanical speed of the machine, the speed at which the shaft of the machine ultimately rotates, is less than that, 1425. What we were talking about, there must always be a difference. N must always be less than synchronous speed. Then we have rotor frequency, rotor current frequency. That one, we gave it as F prime is equal to SNSP over 120. Which is 0.05 times 1500 times 4 over 120, or it is equal to S times sorry, let's just it is equal to 0.05 times 1500 times 4 divided by 120, which is 2.5 hertz, right? That is your rotor speed. And a final one that we have been asked for is shaft torque. So shaft torque is given by tau, which is equals to output power over angular mechanical speed. And angular mechanical speed is equal to 2 times pi times mechanical speed over 60, which is 2 pi times 1425 over 60, which is 2 times this pi times 1425 divided by 60. 149.22 radians per second. Therefore, T load or tau load is equals to output power. So the output power was 7.5 kilowatt. 7.5 times 1000 divided by 149.22, which is given by 50.26 Newton meters, right? So that is shaft torque. Okay, so that's a quick example of some of the principles of induction motors in terms of design. Let me admit somebody else. There was a problem with the audio when I'm speaking or during that YouTube?
The YouTube video.
The YouTube video. or you were not able to hear?
Yeah.
Okay. What will... Hello? Yes?
The video was not clear.
The video is not clear. Okay, I've shared a link to the video so you can go and watch. It's a very short clip and it explains it extremely well. So that's one thing I'd really request you guys to go and watch that. Okay. So let's continue. So the last part of this, we will be looking now at the power flow in induction motors. So now when you look at induction motors, you have various points at which your power changes, right? And we said that the principle of electrical motors is that they take electrical power as an input and they output mechanical power. So the input here, power input, is active power to the stator through electrical supply. In this case, three-phase mechanical or three-phase electrical supply. And the final output that you will get is what we call shaft power, right? And straight away, the efficiency of your machine nu is the output over the input. So as much of the power that makes it through the process of, rotating magnetic field and induction and Lenz's law and all that conversion, as much of it as possible is what we would want to get at the output point. Okay. Now, what are the various stages? So we will go step by step looking at how your machine converts power. So at the first point, you have input going in as electrical power, right? And the first thing that happens is that you have electrical power moving within the windings, the stator windings themselves, the copper windings that we saw. Just show them here again. The copper windings that we saw here, these windings, right? So there's an electrical current flowing through those windings. And anytime you have an electrical current flowing through those windings, you have I squared R losses, all right? So this is your stator current, okay? So that's one form of loss that you have. We call them stator copper losses, or PCL, SCL, stator copper losses. So that's the first loss. So you have your input power, and at the first point, you have some of the power being lost in terms of stator copper losses, I squared R, within the stator windings. Now, as you rotate your windings, or you have your current flowing through your windings, that current sets up your RMF. Now, the RMF is a magnetic field that is set up inside the center of the stator. Now, in order for you to have a magnetic field build up and move within the windings, or rather within the core, you remember we saw the laminations of the core, you would have losses due to the magnetic properties of the core itself. So you have energy that is being used in setting up your magnetic field. So that means you have some more losses in the form of ion losses in the stator. Okay, so these are ion losses within the stator. That is a heat loss due to the properties of the core. So we call that P core. Okay, so far you've not yet even moved your power within the machine. You've not yet even reached the rotor, and already there is some power that has been left. Okay, so this is P core, this is PSCL, right? Already, this is all you're left with. So the active power, after you've lost heat due to the copper and you've lost heat due to the core of the magnetic field, what you're now left with is the active power that can then be supplied to your rotor. So this is the rotor power, and we call that air gap power. So air gap power. The reason we call it air gap is that it is the power that crosses the air gap between the stator and the rotor itself. That's the actual power that is being made available to the rotor for it to convert it into a mechanical energy. So now you have your air gap power here. Remember, once your air gap power crosses over in the form of magnetic field, you now have induced currents being rotating through the rotor. So you have a current IR at a frequency that we talked about, but again, there are losses within the rotor, because the rotor, remember, is a series of copper bars that are there, and there are currents flowing through those bars. So those currents, they cause heat losses within the rotor. So this is called P rotor copper losses, right? So you have rotor copper losses at this point. So PRCL, which are rotor copper losses. Incidentally, PRCL is equal to the slip times air gap power. Yeah, there's a certain amount of power that is lost, and it is proportional to the slip of the machine. So you have RCL losses being felt there. Okay. Now, once you have that, what you remain with is now the total amount of power that has been converted into mechanical form, which is here, right? So you've lost some heating to the copper of the rotor, but you're now left with mechanical power that is available at the machine. And this is what we call converted power, right? So it is mechanical power or converted power. P converted. Okay. So that power is now available at the shaft in the form of mechanical or rotational energy. But once it is at the shaft, there are certain losses that it encounters in terms of windage and friction. So remember, your mechanical power is transmitted through the bearings. Yeah, and the bearings always have friction. So that is some loss that is there. Okay, so in terms of here, our diagram, we have friction, and we also have windage. So the air resistance. But ultimately, what we are then left with is your output power, your shaft power. So that is the sequence of events that occurs when you have power being converted from electrical to mechanical or mechanically useful work. So P in and P out. So before you get from P in to P out, you can imagine that P out is equal to P in minus SCL minus air gap, or rather minus SCL minus stator ion losses minus rotor copper losses minus friction minus air resistance. And at each stage, this air gap power and this converted power are usable in various forms, right? So at this stage, it is at the stator. Let me put this in a different color. So up to this stage, this is the stator. Up to this stage, then you have air gap power, which crosses over to the rotor, still in magnetic form. So this is electrical. This is magnetic. And then finally here it is mechanical at the shaft, right?
Question?
Yes.
I was asking if there's this much loss of power
Yes.
in the motor. I was asking, so how efficient is it in terms
Actually,
of doing it?
yeah, that's a very good question. Induction motors are actually not that efficient. Generally, they'll be 80 to 75% efficient. Now, by various methods, you are able to reduce the losses that you have within your motor. You can change the type of materials that you use so that you have lower copper losses in the rotor and in the stator. In the core, you can change the degree of laminations, you can change the type of material used. It becomes a balance of the cost of the materials versus the efficiency that you get out of them. In terms of friction, you can have different kinds of bearings. In terms of air resistance, you avoid having fans, or you have a more aerodynamic way of operating. However, even after saying all that, even after having all those losses, the losses themselves are not that big. So in fact, let's go ahead and do an example to demonstrate the nature of the losses that we have. So straight away, you have the power input to a machine is all that. Losses, stator losses are 1 kilowatt. That should be a kilowatt, not a kilometer. And friction and windage are 2 kilowatts. Okay. So straight away, you can see the three-phase, it is supplying 40 kilowatts, and stator losses are 1 kilowatt and the others are 2 kilowatts. So let's see what percentages those leave us with. So first of all, we are looking for slip. So that's always the first thing that we do. So in terms of slip, we have, first of all, we get synchronous speed, which is equal to, let's get our calculator. Synchronous speed is equal to 120 F over P, which is 120 times 50 over, this is a 6-pole. So divide by 6, 120 times 50, divide by 6. So it is 1000 RPM. We look for a slip, NS minus N over NS, which is 1000 minus, we were given motor speed as 975 over 1000. So 1000 minus 975 divided by 1000 times 100% gives us 2.5% slip. Okay. So number 2, you want rotor copper losses. So this is, once again, the losses because of the current that must flow within the rotor. Okay. Now here we have an interesting situation whereby we don't know, the rotor is in the middle of the machine. We have not been given all the information that we need, but we do know that the rotor input, which was air gap power, which was here. So the rotor input is this air gap power. And how do you get the air gap power? So you get air gap power by saying that it is equals to input minus stator copper losses, right? Now, in this case, one thing we have been shown here, we are not given core losses. Yeah, we should have deducted core losses, but usually what happens is that they indicate the core losses separately, right? Or rather, they combine the core losses with friction and windage at the end. Okay. In terms of engineering, sometimes it is easier to do that. But for purposes of this example, we are disregarding core losses. So let's just say P core is equal to 0. So in this case, Pi, which is the input, we were told is 40 kilowatts minus 1, which we were given here, 1 kilowatt, minus core losses, which we were told is 0. So this is 39 kilowatts. This is your air gap power. That is the power available to the rotor. And remember, we gave the relationship that, let's go back here. Remember, we gave this relationship that the rotor, the power at the rotor copper losses are equals to slip times the power at the air gap. So here we would be able to say that the rotor copper losses are equal to slip times air gap power, which is 0.025 times 39, right? So divided by 100 times 39. So that gives us rotor copper losses of 0.975 kilowatt. Okay, so it's significant. Stator losses is 1 kilowatt, rotor copper losses is 0.975 kilowatts. It's significant, but not too bad. Okay, so rotor copper losses, right? The third one, we want output power. So output power. So in terms of output power, what do we know? We know that we have reached up to the point of rotor copper losses. We've calculated up to there. So we know, if we go back to our diagram, we know that our rotor copper losses are up to there, and we know our air gap. So that we know, and that we know. So you can find the difference, which is your converted power. So let's look at what is the converted power. P converted is equal to air gap power minus rotor copper losses. But remember, rotor copper losses is equal to 1 over S. So actually, converted power is equals to air gap power into 1 minus S. Okay, because there's a relationship between air gap power and rotor copper losses. So converted power is equal to 39 times 1 minus 0.025, which is equals to 39 minus 0.975, which is 38.025 kilowatts. So that's converted power. So this is the mechanical power that is available at the point of the rotor. From that, we need to deduct the friction and windage so that you are left with ultimately the output power. So the output power is equal to the converted power minus friction and windage. And this is equal to 38.025 minus 2. So output is equal to 36.025 kilowatt. And so finally, we can look for the efficiency, which is...
I have a question.
Yes. Go ahead.
Can we get the power output by subtracting the power input minus all the losses?
Yes, you should. Actually, let's do that experiment. I'm actually curious. So P out is equal to P in minus P SCL minus P RCL minus P F and W minus P. What was the other? There's another. That's it. Yeah, core losses was 0. So it would be, what is our input? 40 minus SCL was 1 minus RCL was 0.975 minus friction and windage is 2. Should come out to the same thing. So 40 minus 1 minus 0.975 minus 2. Yep, it's the same thing. Because that is essentially, you saw the flow. Yeah. So if you can account for all the losses across each stage, you will be able to find out what is your actual output. So finally, your efficiency is equals to 36.025 over 40, which is equal to, it's around 90%. So it's not too bad in terms of efficiency for a machine. It is bearable. 90% is, in engineering terms, not too bad for a machine. Internal combustion engines have way, way less than that. So I guess as a means of energy conversion, it's not significantly terrible. Okay. So I think we'll stop there. Do a bit of reading. There'll be a handout on starting of three-phase induction motors. Let's put it here. So additional work you would need to do three-phase induction motors are self-starting. This is a different kind of starting. This is to do with the initial current that is drawn by an induction motor when it is starting up, right? So look at direct online and look at star delta starting. So there'll be handouts on that. So any questions?
Yes.
Yes.
I was asking, there's usually a difference. As I was doing some research on the motors,
Yeah.
I cut through something like brushed and brushless motors. What is the difference, and in terms of efficiency?
Brushless motors are a different kind of motor. Those are, what is the principle used there? They are now more towards, okay, they are kind of like the reluctance motors we were talking about. Yeah, those are not induction type motors like these ones. In fact, I should add that. So these are the reluctance motors that we talked about. Yeah, they are brushless, they are stepper, sorry, brushless, stepper, and so on and so forth. Those are a different type of motor. I mean, they were not in the scope of this unit, but nowadays they are fairly common because nowadays the materials that are needed, because these reluctance motors make use of permanent magnets. And previously, permanent magnets were quite expensive to manufacture, and so it was not economically viable for you to use them in common applications. But nowadays, due to the technology of creating these permanent magnets having been increased, there are certain materials that have been developed. So they are becoming cheaper. And so, you have things like what you've called the brushless motor and so on and so forth. Those are very common, especially in low power applications and in precision applications. So like actuators and things like that. They are not in the scope of this particular unit, but they are an interesting, I can give some materials on that just for your own reading.